All right, get ready. We're diving headfirst into the world of kinematics,
Kinematics,
the
yes.
physics of motion, basically.
How things move, exactly.
You've sent over some seriously in-depth physics notes.
All PDF excerpts.
Our mission, should we choose to accept it,
We should.
is to break down all these core concepts,
Like speed.
velocity, acceleration,
They're
even
thinking projectiles.
by the end of this deep dive, you'll be,
Physics masters.
well, maybe not masters, but you'll definitely be able to hold your own in a conversation.
Definitely. And what's fascinating about kinematics is that it really focuses on the how of motion.
Yeah, not the why.
Exactly. Like imagine,
Like describing a dance.
yeah, a dance. We're interested in the steps, the speed, the rhythm.
But not like the muscles and the energy involved.
Precisely. It's like watching, say, a figure skater glide across the ice.
Ooh, yes.
We're analyzing their path, their speed, how that speed changes.
But not getting bogged down in the forces from their skates or gravity.
Exactly. It's simplifying motion to its core elements.
Okay, so speaking of simplification, your notes make a pretty clear distinction between speed and velocity,
Ah, speed and velocity.
which I'll admit I kind of use interchangeably sometimes.
Yeah, me too.
Is there really a big difference?
There is. Think of it this way.
Yeah.
Speed is like saying, I'm driving at 60 miles an hour.
Okay.
Tells you how fast you're going,
Right.
but not where you're headed.
Right.
Velocity, on the other hand, is like giving directions.
Uh-huh.
It includes both speed and direction.
Oh, okay.
So you could say, I'm driving at 60 miles an hour north.
I see.
That's velocity.
So velocity is like speed with a built-in compass. Exactly. So if a race car is going around a circular track
Okay.
at a constant speed,
Yes?
its velocity is actually constantly changing
changing because
the direction's changing every second.
that's it. You got it. And
Yeah.
your notes, they even break down speed into different types.
Oh, yeah, they did? You
Uniform,
were.
average, and even instantaneous speed.
Yeah, those caught my eye, too.
What's the difference between, say, average speed and instantaneous speed?
Yeah, what is the difference?
Imagine you're on a road trip.
Okay.
Your average speed
Mm-hmm.
is the total distance you travel
Right.
divided by the total time it takes.
Yeah.
Doesn't matter if you were speeding on the highway or stuck in traffic. It's the big picture.
Okay.
But instantaneous speed, that's
Yeah.
like checking your speedometer at any given moment.
Right.
Tells you how fast you're going right now.
Okay, got it. So average speed is like your overall trip report,
Exactly.
and instantaneous speed is like a snapshot.
Snapshot, yeah.
Okay. Let's shift gears to acceleration.
Acceleration, all right.
The notes suggest it's more than just about going faster.
It is. Acceleration is any change in velocity.
Oh, okay.
So it can be a change in speed.
Like hitting the gas.
hitting the gas,
Yeah.
speeding up,
Or hitting the brakes.
or hitting the brakes, slowing down. Yeah.
Okay.
But, and this is where it gets interesting,
Ooh, tell me.
acceleration can also involve a change in direction,
Really?
even if your speed stays the same.
So even if I'm like maintaining a constant speed while driving around a curve,
Yes.
I'm technically accelerating.
Absolutely. Your velocity is changing
Wow.
because your direction is changing.
I never thought of it like that.
And just like with speed, we can talk about different types of acceleration,
Okay, hit me.
uniform
that
average and instantaneous.
So uniform acceleration would be like a plane taking off, steadily increasing its speed.
Precisely.
Okay. And variable acceleration.
More like a roller coaster.
Right.
Well, it's twists and turns and changes in speed.
Yeah. Okay, that makes sense.
Now, ready to get a little more visual?
Always.
Your notes start talking about motion graphs.
Yes. Displacement time graphs, velocity time graph.
Are these just fancy ways of showing the same info as the equations?
I mean, kind of, right?
They can be,
Okay.
but graphs are actually incredibly powerful
How so?
because they let us see the patterns and relationships in motion.
Okay.
For example, did you know that the slope of a displacement time graph tells you the velocity?
Wait, really?
Yeah,
So a steep line on the graph means the object is moving faster.
exactly. Steep slope means a large change in position over a short time,
Uh-huh.
and a horizontal line
Horizontal.
means the object's at rest.
Okay.
Similarly, the slope of a velocity time graph, that tells you acceleration.
So a flat line on a velocity time graph means
Means,
velocity's constant,
Yeah.
no acceleration.
you got it. And a steep line.
A steep line means rapid acceleration.
Exactly. And here's another cool thing. The area under a velocity time graph,
The area.
it represents the object's displacement.
Whoa.
So by analyzing these graphs, we can extract a lot of information.
But like a visual code.
Exactly.
I'm starting to get it now.
Good, good. And speaking of visual, your notes move on to a really cool topic. projectile motion.
Okay, yes. This is where I start picturing cannons launching balls and stuff.
Classic physics problems.
Yeah, exactly.
Well, projectile motion is basically the motion of any object that's been, launched or thrown.
Like,
Baseballs.
basketballs.
Even the spray of water from a fountain.
Oh, yeah. Oh,
It's all governed by the same physics principles.
So, to understand projectile motion, don't you just gotta, break it down?
You're on the right track.
Okay.
The first thing to realize is that a projectile's velocity has two components.
Two components.
Horizontal and vertical.
Okay.
These components act independently of each other.
Whoa, that's kind of mind-blowing.
It is, isn't it?
Why do we gotta think about them separately?
Because gravity.
Gravity?
It only acts in the vertical direction.
Right.
So the horizontal component stays constant,
Okay.
assuming we're ignoring air resistance for now.
So, if there were no air resistance, a projectile would just keep moving horizontally forever.
Theoretically, yes.
Oh.
It's like that saying, what goes up must come down.
Yeah.
Gravity's always pulling down,
Kind of weird.
affecting the vertical motion.
Okay.
But without air resistance, there's nothing to slow down or change that horizontal motion.
That's incredible. So even though it looks like a smooth curve,
It does, yeah.
it's actually doing two things at once.
It is.
Coasting horizontally and then dancing with gravity vertically.
Precisely. And that combination creates the parabolic arc we see.
Now, this is where it gets really interesting.
Okay.
The notes mention something about the path of a projectile being a parabola.
A parabola, yes.
Why a parabola? Why not a circle or something?
Well, it turns out that the influence of gravity,
Great.
combined with that constant horizontal motion, results in a path that's mathematically described by a parabola.
Oh, wow. It's not just a coincidence.
Not at all. It's a fundamental property of how gravity shapes motion in two dimensions.
Okay, I'm starting to see how it all connects. So by understanding the horizontal and vertical components,
Yes.
we can analyze everything.
Speed, direction, position at any given time.
That's incredible.
It is. And the notes, they go on to define some key terms.
Oh, yeah. The terms time of flight
Maximum height.
and horizontal range.
These all seem pretty self-explanatory, but what actually determines them?
It all boils down to the initial conditions.
Initial
The
conditions.
projectile's initial speed
Okay.
and the angle at which it's launched.
So if I throw a ball with more force,
More force. Okay.
it'll have a greater initial speed, which means it'll travel farther.
Exactly.
What about launch angle?
Launch angle is crucial. For a given launch speed,
Yeah.
there's an optimal angle that maximizes that horizontal range.
Is it 45 degrees?
You remember? Yes, 45 degrees to the horizontal will give you the greatest distance.
Oh, wow. It's amazing how something as simple as throwing a ball has so much physics behind it.
It really is. And there's even more to it.
There's more.
Your notes also mention striking velocity.
Striking velocity.
The projectile's speed and direction right when it hits the ground.
So it's like the grand finale.
Exactly.
We can actually calculate that. We can. It's not as simple as just the initial velocity, though.
Right.
We got to consider gravity.
Right.
How it's changed the velocity over time.
This is a lot to take in.
It is. It is.
We've covered speed, velocity, acceleration,
Rough.
projectile motion, all in part one.
All in part one. I think we need a moment to process.
Yes, agreed. Let's take a break and then come back and dive even deeper.
Sounds good to me.
Okay, I think I've caught my breath. Projectile parabolas.
They are pretty cool.
Who knew they were so fascinating? What other mind-bending concepts are hidden in these notes?
Well, next up is this idea of relative velocity.
Relative velocity.
Might sound a bit head-spinning, but it's something you experience all the time, really.
Okay, I'm all ears. Give me an example.
Imagine you're on a moving walkway at the airport.
Okay, yeah.
You're walking along, someone passes you, going in the same direction. To you, they seem to be moving at a normal walking pace.
Right.
But to someone standing still off the walkway,
Yeah.
that person seems to be moving much faster.
Right, because their speed is combined with the speed of the walkway.
Exactly. It's all relative.
It reminds me of when I try to walk on a train.
Oh, yeah.
It feels normal to me, but to someone outside, I must look like I'm moving so fast.
You would be. And this concept, it can get even more interesting when we think about objects moving in different directions.
Okay, how so?
Think about trying to row a boat across a river.
Yeah, with a strong current.
Exactly, a strong current. It's not as simple as just rowing straight across.
No, it's not. If you want to end up directly opposite your starting point,
Right, if you aim straight across, that current's going to push you downstream.
you'll land at an angle.
You will.
Yeah.
To reach the opposite bank in a straight line, you got to row slightly upstream.
At an angle.
At an angle, yeah, to compensate for that flow.
So it's like a battle of velocity.
The battle, yeah.
Your rowing velocity versus the river's current.
And that's a great way to think about it.
Yeah.
And the resulting path of your boat, it depends on the vector sum of those two velocities.
Now that you mentioned vectors,
Vector,
I remember that term from the notes too.
important concept.
But I'm a little fuzzy on what exactly makes a vector different from a regular number.
It's all about direction.
Direction.
A regular number or a scalar just tells you magnitude,
Magnitude meaning.
like how much of something there is.
Okay.
The temperature's 75 degrees, I have a 10-pound weight.
Yeah.
But a vector includes both magnitude and direction.
Okay.
So velocity is a vector because it tells you not just how fast something's moving, but also in what direction.
Ah, so it's like the difference between saying, I walked 5 miles
Yes.
and I walked 5 miles north.
Exactly. One just tells you the distance, the other gives you the full picture.
And why is this distinction important?
It affects how we combine and analyze these quantities. You can add scalars directly, no problem.
Like 2 pounds plus 3 pounds equals 5 pounds.
Exactly. But with vectors, you can't just add those magnitudes together. The
Different.
directions matter.
Right, right. So like if you walk 3 miles east and then 4 miles north,
You haven't walked 7 miles total.
no, you're somewhere northeast.
Exactly. To figure out that final displacement, you got to use vector addition,
Which takes into account,
both magnitude and direction.
okay, I'm starting to see why vectors are so important.
They're everywhere.
Relative velocity, projectile motion. It's like they're the secret language of physics.
You could say that. And your notes, they dive even deeper, introducing those famous equations of motion.
Ooh, equations I'm ready to get my math on. Are these like secret formulas
They are.
for unlocking the mysteries of motion?
They allow us to predict an object's position, velocity, acceleration,
At any given time.
as long as we know the initial condition.
And the acceleration.
Exactly. So let's say you know how fast a ball is thrown.
And the angle.
You can use these equations to figure out where it will land.
That's some serious predictive power.
It is, based on some pretty fundamental principles.
Like Newton's laws.
Exactly. But there's a catch.
The catch.
These equations generally work best in idealized situations,
Me-
like ignoring air resistance.
Right. Reality and physics don't always see eye to eye.
That's true. But let's stick with the ideal for now.
Okay, so tell me about these equations. What are they?
They're often called the SUVAT equations.
SUVAT.
It stands for the variables they use. S for displacement, U for initial velocity, V for final velocity, A for acceleration, and T for time.
SUET. Okay, I'll try to remember that. So what can we actually do with these equations?
Let's say you drop a ball from a certain height.
Okay.
You know, the acceleration due to gravity.
Right.
You want to know how long it'll take to hit the ground?
You can use one of the equations to solve for the time.
Exactly.
That's amazing. So it's like having a mathematical toolkit
Toolkit, yeah.
for predicting how things will move.
And they're incredibly useful for analyzing all sorts of motion.
From simple free fall to projectile motion.
All of it.
This is really starting to click for me now.
Good, good. And speaking of breaking things down,
Yeah.
your notes emphasize the difference between vectors and scalars.
Right, scalars are just magnitudes, like speed or temperature.
Exactly.
But vectors have both magnitude and direction.
Like velocity.
Right, right.
And this difference has huge implications for how we handle them mathematically.
With scalars, you just add them up, easy peasy.
But with vectors, you got to consider those directions.
So it's not as simple as just adding two numbers together?
Not always.
Yeah.
Think about forces acting on an object.
Okay.
If two forces are pulling in the same direction,
Yeah.
you just add the magnitude.
Just find the net force.
But if they're pulling at an angle,
Oh.
got to use vector addition,
Which takes into account both.
both magnitude and direction. It's crucial.
I'm starting to see how neglecting that vector nature could really mess things up.
It would. It'd be like navigating with only half a map.
Wow, this is a lot to process.
It is. We've covered a lot.
Relative velocities,
Oh.
rowboats, equations of motion, vectors.
We have.
My brain needs another breather.
Let's pause here and then come back for the final part of our deep
A
dive,
final part.
where we'll explore how vectors can be used to unlock even more insights into motion.
We're back. Ready for the final part of our kinematics journey? It's amazing how much depth there is to motion.
It really is. And we left off talking about vectors.
Vectors, right? I'm ready to see how they can help us unlock even deeper insights into all this.
It's amazing how much information is packed into those little arrows, isn't it?
It is. So, spill the beans. What kind of vector magic are we talking about?
Well, one of the most fundamental things is vector addition.
Okay, vector addition.
It's basically a way of combining vectors to find their overall effect.
Right, but we can't just add them like regular numbers.
Nope, got to consider those directions.
So how do we actually add vectors then?
One way is using the tip-to-tail method.
Tip to tail.
Imagine you've got two vectors, A and B.
Okay, A and B.
You draw vector A.
Mm-hmm.
Then you place the tail of vector B right at the tip of A.
Okay.
The vector that goes from the tail of A to the tip of B, that's your sum.
So it's like creating a chain of arrows.
That's a chain, yeah.
And that final arrow represents the total effect.
Exactly. And the order you add them in doesn't even matter.
So A plus B is the same as B plus A.
You got it.
But things get a bit trickier when the vectors aren't pointing in the same direction.
Definitely. If they're at angles, we got to break them down.
Break them down into like smaller vectors.
Into components.
Components, right.
Let's use trigonometry.
Sine, cosine, tangent.
All that good stuff. To find the horizontal and vertical portions of each vector.
So like projecting their shadows onto the axis.
Exactly. Then we add the horizontal components together and the vertical ones together.
And then
we use the Pythagorean theorem
right.
to find the magnitude and direction of the overall vector.
Okay. A bit of a process, but I think I'm following.
Good, good. Now, how does this all connect back to motion?
Yeah, that's what I'm wondering.
Remember projectile motion?
With the horizontal and vertical components of velocity.
Those are vectors.
Oh, right.
And to analyze the motion at any point?
We can use vector addition.
Exactly. To combine those horizontal and vertical velocity vectors.
So at any moment during its flight, the projectile has these two vectors, and we can add them together.
To get its overall velocity vector.
Which tells us the speed and direction at that moment.
You got it.
This is amazing. It's like piecing together a puzzle using vectors to see how the motion is evolving over time.
And this applies to other scenarios, too, like the boat crossing the river.
Relative velocity.
We were essentially using vector addition there, too.
To combine the boat's velocity with the current.
Precisely.
This deep dive has been incredible.
It has.
I've gained a whole new appreciation for physics.
Me too.
Yeah.
And we've just scratched the surface.
There's so much more to explore.
Forces, energy, relativity.
I'm definitely feeling inspired to keep learning.
That's the spirit.
Thanks for guiding me through this deep dive. It's been amazing.
You're very welcome. Remember, curiosity is key.
Curiosity is key. I like that. Well, on that note, we'll wrap up this deep dive into motion.
Until next time.
Until next time, keep those brains buzzing.